Let's look at the bridge rectifier in context of a power supply. This is an Elenco XP-660. I have one of these. This is a 5-volt fixed output, 5 amps maximum output power supply, and this is just the section of the schematic with the 5-volt output. Remember, we have, as part of this, we have a transformer, switch and fuse and such, diode rectifier. In this case, it happens to be a bridge rectifier. And then we get to a filter, which is just a large capacitor. Here's what this looks like. Here's what this looks like for us here. All right, so here's our bridge rectifier. You know it's a bridge rectifier, one, by seeing the diodes and how the diodes are connected and used. That's what makes it a bridge rectifier. Also, this says BR1, which perhaps stands for bridge rectifier. MDA 2501, this is a old part. Bridge rectifier shows up in one package with 4 terminals in it, all 4 diodes together. Ubiquitous, and they might be out of production now, I'm not sure. Pretty close. This transformer has 4 secondary windings. We're going to be concerned only with this secondary because this is the AC input to this this bridge rectifier. All right, so that's our input to this. I'll just put a box around here. I'll say rectifier. Always right after the rectifier is our filter capacitor. Turns out that there's 2 capacitors in parallel. Okay. And here's another place where I can go off on this rant about ground symbols. You see how that these capacitors are hanging out nowhere? Well, this minus means it's a minus terminal labeled minus, whatever that means. This is hooked together is what the schematic is telling you. It's also saying that this terminal is attached. Okay. All of these, it's also tied to this node and this node and this node, and if you see that this node over here is attached to the GND, the bottom side of the 5-volt power supply's output. For now, I'm just going to keep these connected together, but it makes the schematic a little clearer, but circuit analysis gets a little more difficult unless you're just clearly aware of that. My opinion, I keep right on the front page of my website thing, agnd.net. All right, so we have this. We have a rectifier, two things here. So we have coming out here. What are we analyzing here? All right, so we want to look at the waveforms that show up in this circuit. Remember, we have, this is an AC waveform. I'll call this VS. All right, but VS, remember, is a waveform that looks like this. Use black to make an axis. Here's this, here's VS. VS really looks like it goes up, goes down, goes up, goes down, right? It's an AC waveform, goes around 0. Well, what's 0? 0 is where you put the plus and the minus on here, and it goes through 0. Do you notice, please notice how neither of these 2 nodes is attached to 0. It's the feature of a bridge rectifier, and they don't need to be, because this is just a magnetic connection in the transformer to get this waveform to show up. However, when we do this, we'll say this is, 8.3, 8.6, 17, 35, I don't remember. All right, so this is some number. I think it was 8.6 volts RMS. Whenever we see AC waveforms, we usually talk of them in root mean squared. We're going to assume this is just a single frequency, 60 hertz signal. But this is RMS. What we need is actually need the peak value. Remember in the last page that we were looking at the peak value here. That peak value, this is 8.6 volts RMS. This peak value is V peak is 8.6 volts, or whatever the RMS value is, times the square root of 2. I've got another handout that talks about how we get the square root of 2. Think about RMS and sine wave. Square root of 2 always pops up in your head. Remember, you got to multiply by it because the peak is always bigger. Why the square root of 2? It is specifically because of the shape of this waveform. Because it's a sine wave, we get the square root of 2. Other shapes will get you other factors here, so watch out. It's not always, RMS is not always square root of 2. So this goes up and down. We have this peak value of some number of volts. And that's going to show up between here and here. In the last page, we said that this voltage that was going to show up here, specifically between, oh man, this one here and here, that is, this is V raw. Of course, it's the same as this voltage on the right side of this capacitor. V raw, the very peak value of that is going to be V peak minus 2 VD on, and that was from the previous page. This is page 2 of my handout. All right, so V peak, whatever this is, if you want to calculate this out, I think this was 8.6. I really don't remember the number, and it's not important at this precise moment. Remember, convert to peak from RMS. All right, at this moment, we're going to be drawing current out of our circuit. And what do I want to do? This one, current's going to be going this way. This whole circuit right here. And you can debate whether that last capacitor is part of it or not. I'll go this way. Here, this is a voltage and current. Voltage and current regulator. This says IC 1723. Could be an MC 1723 is what it's actually labeled in the schematic. Others may know this is it's another clone of the LM 723, or the really classic UA 723. Classic circuit. Add some more parts, and now you have a regulated power supply. It's worth knowing what goes on inside of here, but for where we are in the class for electronics, we just identified that this is a voltage regulator. The output terminals are here. This is, I would consider this an additional filter, and not exactly part of the regulator. It's not quite needed. All right, so we have our current flow through this is going this direction. I'll just draw this path. The large current, the 5 amps that's attached here, goes from collector to emitter of this, and be careful. This is part of the regulator circuit. The large currents that you need large wires is going this way. Okay, and then we go out to our load here. We have the load. This is another thing that I don't like in this schematic especially. So this is 5-watt power rating. It's 2, but this is, see that dot? It's really small. It says 0.14. This is really 0.14 ohms. But man, I would just go 0.14, or an even better way would be 0R14 to name that, which is 0.14 ohms, or in parallel, this is 70 milliohms. All right, there's 5 amps maximum flowing through this. This resistor is also part of our current measuring circuit. Comes back here to pin 3, and that's current limit. What else? Okay, so if we look at this, I'm going to attach a load here. And we'll just take our load to be a current sink, I would call it. A current sink, I like to call it that because it's dissipating power, perhaps. All right, we add that onto here. We're going to look at the waveforms of this. that happen here, and this waveform looks like this. Here's time. All right, and we have V out. All right, V out, and here's 5. All right. Well, this 5 amps is flowing this way. This is 5 amps, and it's flowing through this transistor. The voltage across this transistor is going to change over time because that's what the regulator's job is. It's this pin 10 and such. But also you can say that basically the current flowing out of this is 5 amps continuously. But remember, current's only flowing when these diodes are on, and these diodes are not on all the time. I'm going to really exaggerate this waveform here. It goes up, and then we're going to go down, and it goes up. There's another video that really shows this again, and I want to have it in this video too. All right, our bridge rectifier is going like this. It goes up, it goes down. The other one, remember, okay, then the voltage across this thing, this is totally not to scale, goes up, down, up, down. So in this thing, the diodes are on. In this region, diodes are on. This region, diodes are on. And then in this time, it's off. These diodes are off as well. During this time, if we look here, all of these diodes are off. There is 5 amps flowing out of this capacitor at one time. So we have a capacitor with an initial condition. I think this is a 10.5 volts I measured on average, and then we have a 5-volt source. We look at this and we know this is just going to discharge. Start from initial condition, and then the voltage across this is going to discharge. We can see that if you put a probe on this one. The output is going to stay the same because of the action of the regulator. It's going to remove all of that ripple. We'll move on to the next section next.